day. We're going to be discussing the periodic table and trends. It would be super helpful if you have a copy of the periodic table available to you. I'm going to be using one on the overhead here. You can print out a whole lot of periodic tables if you don't have one of your own to use, or you can't find a good one on the internet. Email me and I'll send you one of my favorite ones. If I can remember to do that, I will also post one so that everybody can have a similar version. All right, periodic table. Here we go. Mendeleev was a Russian chemistry teacher, and at the time, the turn of the century, they didn't know a lot of elements. They had a couple dozen that they knew about, mostly because of the work of the alchemists. And the alchemists were scientists who, back at that time in history, were trying to turn base metals into gold. They tried lead and tin and nickel and some of the other base metals, and they did all kinds of chemistry to these base metals and added them to different elements and formed new substances, but of course, as you probably have realized at this point, they were never able to get them to turn to gold. Well, this turned out to be very helpful for Mendeleev because he had all this information about each of the elements and their reactivities, and he categorized the information that he had about each of the elements onto little cards, sort of like a solitaire game, and he put them on little cards, and then he started juggling them around, and he came up with the basic organization of the periodic table that you see here. This is his version of the periodic table, which consisted mostly of the representative or group A elements. He predicted the existence and future discovery of new elements using this same method, and that was his major contribution. Not that he discovered any of these elements on his own, but simply that he looked at trends on the periodic table, looked at what was available, and then figured out that there might be elements in certain places that had a particular type of chemical and physical characteristics. This idea that Mendeleev came up with was the periodic law, and he said that things organized on the periodic table are ordered according to increasing atomic number. And that's why you see things like hydrogen and helium, 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on left to right, like reading a book, much like what you would do with electron configuration. So in the vertical column on the periodic tables are the groups or the families. The horizontal columns, or horizontal rows on the periodic table are called rows or periods. That's why it's called the periodic table of the elements. If we're going to look back at our periodic table in the same way and look at where these groups of elements exist on the periodic table and what they look like. All right, so these, the vertical columns, are the families or groups. And they call them families or groups because they share similar physical and chemical characteristics. So this group here, this first group, hydrogen, lithium, sodium, potassium, rubidium, is called the alkali metals. And yes, you do need to know their common name. Group 2, this group here, beryllium, magnesium, all the way down to radon. Group 2 is called the alkali earth metals. Over here, on this side of the periodic table, this family or group here, a lot of people know this one already, this is known as the noble gases. And this family or group is also another relatively famous one, the halogens. All right, so those are the common names that you absolutely need to know from the periodic table. The rows or the periods are these groups that go horizontally on the periodic table. So these are rows, also called periods. And rows or periods can be 1, 2, 3, 4, 5, 6, or 7, which of course, as we talked about in electron configuration, correspond to the energy level where electrons can be found. There's 18 groups on the periodic table. Generally, we use the designation where A and B elements are called the representative elements or the transition elements. So if we look at that on our periodic table, the representative elements are this block here and this block here. So those are group A elements, also called the representative elements. And you can see group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. This block in the middle here These are the group B elements called the transition element. These are the representative elements, also known as group A or group B elements. So those are another designation on the periodic table that you need to be aware of. They did change it a little bit and added the IUPAC uses 1, 2, 3, 4, 5 instead of the A and B designation. We prefer A and B generally here in the United States, but most of our periodic tables are marked in both conventions. All right, representative, transition. The intertransition elements, also known as the rare earth elements, is this group down here, the F block of elements. And you can see the numbers 57 through 71 fit right in there. So if you look at your periodic table, you can see the numbers 57 to 71. That's where this group here called the lanthanide series fits right in that section. This is the actinide series, elements 89 through 103. You can see that they go in right there into this section. So this whole block, the lanthanide series, fits in right there. You may have seen some odd-looking periodic tables that don't look like the ones that we use, and those are the ones that are going with taking those intertransition elements and putting into those two blocks. So those are the lanthanide and actinide series. Those are the common names. And now we're going to get to periodic trends. And trends have to do with things that we already know based on electron configurations. Trends also have to do with position on the periodic table. The first important trend we're going to look at is atomic radius. And if we look at radius in general as a geometric term, remember radius has to do with a circle. And radius is the distance from the center to the outside point of the circle. So that's the radius. So if we look at the periodic table, a clean copy here, we look at the periodic table, we look at trends on the periodic table, it makes pretty good sense that periods 1, 2, 3, 4, 5, 6, or 7, the elements in those rows are going to get consecutively larger as you go top to bottom because they have more energy levels, right? We talked about energy levels here. We got a nucleus, we got the energy level n equals 1, 2, 3, and so on. So trend in size of atoms, and I want to capitalize atoms. That means they are ground state, because as you might imagine, if you lose or gain electrons, that's going to change the size. So if you're using this trend to make predictions on the periodic table, the trend on the periodic table, and here's our shadow box outline, which makes total sense, is that size of atoms, and remember these are atoms, not ions, size of atoms increases from top to bottom. We'll make a little graphic there to help you remember. They start small, they get bigger and bigger and bigger as you go top to bottom on the periodic table, which makes a lot of sense because you've got additional energy levels. The trend that doesn't make much sense is the trend as you go left to right. The size is actually opposite what you might expect. So the size increases in this direction. So they start large and they get smaller as you go left to right, which doesn't make as much sense. And you go, I wonder what's going on there. Why, if we're going in the same row? Because keep in mind, we're adding electrons to the same energy level. You would think they would either A, stay the same size, or B, get slightly larger to accommodate the fact that you have additional electrons. Well, let's just look at the third row, n equals 3. If we look at sodium, sodium's atomic number is 11, right? So if we look at sodium, which is here, sodium's atomic number is 11. That means it has 11 protons in the nucleus. And the protons in the nucleus give us what is called the effective nuclear charge, which means those 11 protons in the nucleus of the atom are pulling on to all of the outer electrons that surround that atom. So something like sodium, which is in the third period, compared to something like argon, which is also in the third period, which still only has 3 energy levels or shells of electrons, has an atomic number of 18. So Argon over here has 18 protons in its nucleus. Well, an effective nuclear charge of 11 versus an effective nuclear charge of 18, 18 wins, which means this is more positively charged nucleus. So those layers of electrons that we have spinning around the nucleus, when you have a plus 18 charge instead of a plus 10 charge, it's pulling on those electrons a little bit tighter, so it actually makes the atom radius shrink down a bit, so that gives us the size. So if you wanted to summarize the size trend on the periodic table, size of atoms, and remember it's atoms only, is that direction. That would be a good thing to put on your periodic table, or excuse me, on your 3x5 card for the next exam, because I may give you things like, who's bigger, an atom of calcium or an atom of copper? If we look at calcium and copper where they are on the periodic table, there's calcium, there's copper, they're in the same period, but because copper is further to the right, it's actually going to be smaller than calcium, so calcium would be larger. If we compared beryllium with calcium, calcium would of course be larger than beryllium because it's further down in the row. So if you want to compare size of atoms, is this trend here. The next trend we're going to look at is ionization energy. Actually, you know what? Let's go back to the PowerPoint because I think we've got some information there. All right, so radius decreases and decreases or increases the way I've shown you. There's a nice graphic which shows the relative comparison of the atoms together. Now, once again, I'm going to remind you, this is atoms, not ions. As you might expect, when you lose electrons from your valence shell, and that's what happens when you form a positively charged cation, when you lose an electron from that valence shell, it becomes a bit smaller. When you gain an electron in the valence shell, it becomes a smidge larger. So the trend only works for atoms, not ions. There's another nice graphic that shows you how the sizes change. And we've already talked about the shorthand electron configuration. So why do we care about valence electrons? Because that's where the action is going on. And I believe we already said that in representative elements, the valence electrons is simply the same as the group number. Let's double check and make sure that we understand that. All right, so remember representative elements are the ones in red here, this block here and this block here. So if we look, group 1A has 1 valence electron, 2A, this group has 2, 3A, this group has 3 valence electrons, 4A, this group has 4, and so on to the noble gases, which have 8 valence electrons. So for the representative elements, the group number is equal to the number of valence electrons. And that's why I put that information on a single slide by itself, because it's important enough that it merits having that information on a single slide. We do need to write electron dot formulas for these elements, because that's going to lead us into electron dot formulas for compounds in the next chapter. So we have to learn how to write them for individual elements first. All right, so go back to the projector. We want to write electron dot formulas. We're going to have our basic symbol for the element here. And then we're going to put the dots that display the valence electrons in one of 4 areas around. And you say, okay, it starts 1, 2, 3, 4. Those are the first 4 electrons. And then 5, 6, 7, 8. So, for example, we look at carbon. Remember, we're only depicting the valence electrons in the dot formulas here. This is not a full-on electron configuration. Carbon is here. It's in group 4. So what that means is carbon has 4 valence electrons. So I would put 1, 2, 3, 4. Easy peasy. Let's try another one. Let's try nitrogen. If we look at nitrogen, nitrogen is in group 5, which means it has 5 valence electrons. 1, 2, 3, 4, 5. All right, not too bad. Once we know valence electrons, we have to look at trends in a new topic, which is called ionization energy. And as you might imagine, when you remove an electron from an atom, in this case we took sodium as an atom, that's its ground state atom, It requires energy, so I'm putting energy on the left side of the equation. And what comes out the other side is a sodium cation with a +1 charge and a free electron. So it costs you energy to remove an electron from the structure of a ground state atom. All right? So if we look at trends on the periodic table, I'm going to summarize the trend first in size of atoms. Number size of atoms increases in that direction and increases in that direction. Ionization energy is the exact opposite. You go, well, that's interesting, and that certainly helps us to make some predictions of trends, but let's think about why that happens. Remember with our graphic, as you go down on the periodic table, the radius of the atoms gets larger. So ionization energy shows us that it costs the least amount of energy to break an electron off of the largest atom. It costs you the most energy to remove an electron from a small atom, and that's because of the fact that the closer the atom's electrons are to the nucleus, the harder it's going to be to remove them. So if we have, here's the nucleus, we've got energy levels with electrons spinning around on the outside. The electrons here are so much further away from the nucleus, they don't feel that effective nuclear charge as much. They also are shielded by these other layers of electrons. So there's two things going on here. There's the distance from the nucleus. The further away you are, the less it feels that positively charged nucleus, so it's easier to take the electron off. But also you've got these layers of negative charges in between the positively charged nucleus and the valence electron where those electrons are removed from. So the shielding effect comes into play. So the least amount of energy is required to remove electrons from the largest atom, and that's why the trend in ionization energy is exactly the opposite, the trend in size. There's the ionization energy trend. If we took and graphed a table of the numerical values of ionization energy versus atomic number. So here's atomic number. On the periodic table, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to the heaviest one here. So they're starting at 0 here and plotting them all the way up to 90. And then this is the amount of energy, the ionization energy side of the axis, that tells us how much energy is required. If we look at the peaks at each of those points, the peaks correspond to helium, neon, argon, krypton, and xenon, which are the noble gases. And they cost you the most in ionization energy because they have what is called the true octet. The octet rule is what atoms want to have in their valence shell. They strive to have 8 electrons. If they have to give some up to get 8, or if they have to grab some from somebody else to get 8, that's what they want. So it's real difficult once they do have 8, like the noble gases, to remove an electron from them. So the highest points in this are going to be the noble gases. The points directly below them would be the halogens. The halogens have 7 valence electrons. They want one more real bad. It's going to be doggone hard to remove an electron from something that has 7 and wants one more. So that would be the second one down, and so on. The points at the bottom of the ionization energy graph, lithium, sodium, potassium, rubidium, cesium, correspond to the alkali metals. And that's because there's only one lonesome electron in that valence shell. It's relatively easy in comparison to remove it, so the amount of energy required to remove an electron from the alkali metals is considerably lower. The trend for ionization energy is the same as electron affinity, but we talk about these things in relation to 2 different types of elements on the periodic table. If we look at the periodic table here, we say, remember, metals and nonmetals are separated by a stair-step line. So these are the nonmetals, and these are all the metals. And other than aluminum, if they have 2 sides touching the stair-step line, then they're considered semimetals or metalloids. The metals tend to lose electrons to become positively charged cations. And that's because most metals in their valence shell have only 1 or 2 electrons. Remember, these all lag one behind, so they're actually in inner shells. So most metals have only 1 or 2 valence electrons. In order to get to an octet, if they lose 1 or 2, then they reveal a full shell. So that is their motivation. They lose electrons. So generally with metals, we talk about ionization energy. So we talk about what happens to metals in terms of ionization energy. Nonmetals, on the other hand, they don't want to give up electrons because they have 4, 5, 6, 7, and 8. They want to gain more to gain the octet. So generally they tend to gain electrons to become negatively charged anions. We talk here about what's called electron affinity. And we discuss electron affinity when we're talking about nonmetals because that's the propensity or the tendency that an atom has to grab electrons of other elements. So ionization energy we discussed for metals, electron affinity we discussed for nonmetals. Electron affinity is the same as the trend for ionization energy. We also call it electronegativity. So electronegativity, it's sometimes called, or electron affinity. Right? I have a great affinity for dark chocolate. That means I really like it. So if you have an affinity for electrons, that means you really want them. So ionization and electron affinity follow this trend, right? Size of atoms follows the outer trend. So that thus summarizes a whole lot of information from this particular chapter. All right, so ionic charge has to do with how many valence electrons something has. Now, just because an element tends to lose or gain electrons doesn't mean that it always exists as that charge. All elements on the periodic table in their ground state exist as neutrally charged atoms, right? All of these are neutrally charged right now. If we're going to talk about calcium, it's calcium with a 0 charge. If we're going to talk about oxygen, it's oxygen with a 0 charge. However, when these elements form ions, they form ions in such a way that it's very predictable. So if we look back on the periodic table here, since the alkali metals have a single valence electron, they tend to form ions with a +1 charge. So what I often have students do at this point is take out a clean periodic table, and at the top of this column, you're going to put a +1 and circle it. And you go, well, how's that going to help me? It's going to help you a ton in the next 2 chapters, so you need to know that. So all of these have a +1 charge when they make ions. Now that does not mean that they always exist as +1 charged ions. That just means that when they do form ions, they form ions with a +1 charge. Sort of like that commercial where they talk about the guy that drinks beer, and he doesn't always drink beer, but when he does, he drinks Dos Equis. All right, so these don't always form ions, but when they do, they form ions with a +1 charge. Same is true with the alkali earth metals. Since they have 2 valence electrons, they don't just lose 1, they lose both of them. And this group of elements, the alkali earth metals, always, when they do form ions, forms ions with a +2 charge. Once again, they're not always drinking beer. They're not always forming ions, but when they do, they form ions with a +2 charge. There's only 4 other metals that only have a single ionic charge. All other metals can form ions with more than 1 charge. Like iron can be +2 or +3. Nickel can be +1 and +2. Copper can be +2 or +3. So there's only 4 other metals besides these 2 groups, the alkali metals and the alkali earth metals, and that's aluminum, which is always +3, so put a little +3 in aluminum's box and circle it. Zinc and cadmium are always +2, so put a little +2 in their box. And sodium is always +1, so you're going to put a +1 in those boxes. So those are the 4, other than those 2 groups. So to summarize, if we're looking at metals again, remember metals are everything to the left of the stair-step line. So there's only certain metals that only have a single ionic charge. These can only form ions with a +1 charge. I'm running out of battery juice, but that's okay. I'm almost done. These can only form ions with a +1 charge. These can only form ions with a +2 charge. And these can only be +3, +2, or +1. And then electron configurations for ions. You're going to take away electrons from the valence shell or add electrons to the valence shell. Those are some good examples. You can see here in this example, that's the regular electron configuration for sodium. When sodium becomes an ion, it loses an electron, but it loses an electron from its valence shell, in this case the 3s1 electron. A negative ion, O gains 2 electrons, and it gains them in the shell that it has room for. So let's look at some of those kind of things if we're going to write electron configurations for something that's a little more complex. Something like, for example, iron with a +2 charge. Regular iron, if we look at the periodic table and wanted to write the electron configuration for regular iron, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. All right, so there's the electron configuration for iron. If we want iron +2, it has to lose valence electrons, which are those right there. So those would go away, and the electron configuration for iron +2 would be this. Missing those 4s electrons. So keep in mind, the valence electrons can be a little tricky. If it's something that's relatively straightforward, the valence electrons in something like sodium are easy to figure out, right? But something that's a little more complex, like the inner transition elements, is a little bit more dicey. All right, so that's the end of this